the instrument UV-Vis spectroscopy. This technique is often called as general technique because most of the molecules will absorb the UV-Vis wavelength range, which is the UV region range between 190 nanometer to 400 nanometer, while the visible region is from 400 nanometer to 800 nanometer. This technique can be used for quantitative analysis and also qualitative analysis. This technique contains 5 components, which is the first one is light source. Light source that we are normally use is a combination between tungsten and deuterium that gives the wavelength range from 200 nanometer to 800 nanometer that will pass through the monochromator, and then the light exit from the monochromator with intensity I0 enter the sample. Some of the light that pass through the sample and it exit with intensity I to the detector. Detector will analyze the data and transfer to the meter. After that, the absorbance spectrum will be shown in the screen of the instrument.
For the starting of the experiment, I'm going to take out the clean white tissue to wipe off the clear window of the cuvette to prevent the contamination and the dust. And I will take the frost window. Then I will power up this UV-Vis by power on, waiting for it warming up for a few minutes. Okay, now I am open the cover. This one is the blank. I will put it at the B side, and the hole must be same with the clear window. This one is a blank. I put it at the first place, same as the window must be same with the hole. Now I will click the test, and then I will select the scanning and enter. Now I will choose my test name, enter, and I put it as 1, enter, and then I will select the wavelength. For example, my starting wavelength is 300, and then my stop wavelength, for example, is 700, and then the interval is the speed for the pass between two wavelengths, so it will be 1 nm, and the left one is the automatic. So I will save the test. Maybe you can save it in your USB drive or internet test, and then I will run the test. Select the baseline, and I must make sure that this is the blank. I will select one, which where my sample put. When it's tuned to channel 1, I can click the measure sample. I can find out the maximum wavelength by click on the tabular. The method for find the highest wavelength, you can also click on the edit graph, and I click math, and I click the peaks and valleys. The label peaks you must click on, then the features you select 1, enter. Then you can click on the escape, for it will show automatically the highest wavelength. So we can see the highest wavelength at here is 667 and the absorbance is negative 0.009. Now I have found out the maximum wavelength. I click escape. Escape. To return back to the main, and then I can select the wavelength into just now what I have found. I click the set NM, change my wavelength into 667 and click enter. And make sure this is on absorbent, this is on the blank. I will measure the blank. Make sure it will on the 0 absorbance. Now I will select the one where is my sample on until it changes into cell 1. Show automatically is negative 0.005 absorbance. After I finish my result, I will take out my sample and the blank and I will wash it for the further using of the next user. Thank you.
Today, I'm going to talk about sources of error. First is environmental factors such as temperature and humidity, which can lead to wavelength dependent responsivity changes. Second thing is drift of the spectrometer response. This effect leads to the change in the spectrometer response, not the baseline of the spectrometer. Second is overcome. Overcome is the repeatability contribution to uncertainty, which can be efficiently reduced by repeated measurement for at least 3 times to obtain the accurate result. Got glass cuvette cell, which is this glass cuvette cell. So this glass cuvette cell used in visible range absorbs significant amount of radiation of wavelength below the 320 nanometers, and it is easy to absorb compared to this, which is plastic cuvette cell, because this plastic cuvette cell might containing material component that might interfere with the result of sample. And now I'm going to talk about the component of the cuvette cell. It consists of 2 parts, which is clear part and a bit like not a clear part. So this is the white. So this is the clear part, while this is not the clear part. So before we use this cuvette cell, we make sure that it's in a proper conditions, like there is no like scratches at that clear part, so that later when we use for the analysis, it do not interfere the radiation. So now we're gonna move to that sample. After we fill up this cuvette cell with sample, we have to wipe it with the used delicate task wipers, which is this box. It's contained that wipers which we used to wipe this clear part. While we wiping the clear, we have to wipe the clear part, so we use the wipers just now to wipe the part like this with our both fingers. After we wipe, make sure there is no any stains around that clear part before we put inside that spectrometer. So this is the reason, because it can affect the transmission of the light in the instrument and cause deviation in absorbance reading. So that's why we make sure there is no stains at the clear part and before we put inside
The concentration of an unknown solution based on the absorbance and the concentration of the standard solution. From the absorbance and the concentration of the standard solution, we plot a calibration curve, and the concentration of the unknown solution can be determined by the absorbance obtained from the instrument. For example, is the absorbance of the unknown sample is here, and then we just get the concentration from the graph, and the concentration would be here, and the concentration would be here.